Okay, so in the last class, uh, we discussed the variational formulation for multi-axial equilibrium equation. Today we would like to see, we also made some progress, so we can do finite element formulation. So today we will do our first two-dimensional element. Uh, okay, so so the most elementary two-dimensional geometry that we can think of is a triangle. Okay, and this is the three-noded triangle element. So it has three nodes, 1, 2, and 3, and this is a single element. Okay. Now, one problem that we didn't come across when we were doing one-dimensional problems, the fact that uh, there is so-called triangulation error, or so-called error in getting the shape of the geometry. With one dimension, we could at least accurately get the geometry. I mean, we were getting approximate solutions, but the geometry itself was accurate. So if we were to model a barred element, a barred geometry with multiple barred elements, we were getting the accurate geometry. But when it comes to a two-dimensional problem or three-dimensional problem, we now face the issue that we probably are not able to model the geometry itself accurately. Obviously, refining the mesh, okay, as you can see over here, refining the mesh might improve the amount of accuracy with the modeling of the geometry, but there would still be some error in modeling of the geometry. So with 2D or 3D problems, the accumulation of error starts from the modeling of the geometry itself. So you can see the boundary is curved, but you are trying to model it with a straight edge, and obviously you are getting a different geometry. So now, since we are in 2D, for each node we will be having 2 degrees of freedom. We'll call them U1, U2. So one along x-axis, the other one along y-axis, or horizontal and vertical degrees of freedom. Then there are U3 and U4. I should be using small u because these are all elemental degrees of freedom. U5 and U6. Okay. Now, the coordinates of each node would be x1, y1, x2, y2, x3, y3. Okay. Now, the only reason we used natural coordinates even for our one-dimensional problem was that we can smoothly incorporate that when we are doing multi-axial problems, and that's why the use of natural coordinate proves to be more effective. So that is what we are going to do now. We are now going to introduce the natural coordinates. Now this time we have two natural coordinates. Okay, because it's a 2D problem, so we need two natural coordinates, xi and eta. Okay, and this is our ideal triangle looks like in natural coordinate. So it's a right angle triangle. Okay, and these are its nodes 1, 2, and 3. Okay, now a physical point P over here with coordinates x and y maps to, let's say, P prime at xi eta. Okay, and we will discuss how the mapping occurs, but let us first define the shape functions. Now, there are three nodes. Okay, uh, so what we can think of, there should be three shape functions. Okay, now any interior point within the element, okay, uh, either its coordinates, I mean it is also going to be an isoparametric element. So either its coordinates or its degrees of freedom, let's say uy and ux, they are dependent on the coordinates, the respective coordinates. That means the x coordinate on x coordinate, and they're dependent on the respective coordinates and the respective degrees of freedom of the nodes. Okay, so the shape functions. So there should be three shape functions, and this is how we can map the x coordinate of point P as n1 x1 plus n2 x2 plus n3 x3. Okay, and same thing I can do that for y. Okay, so I can write n1 y1 plus n2 y2 plus n3 y3. This whole exercise can be written like this. Now this time x is represented as a vector, which basically means it's a coordinate vector, and this is how it must be written. For any interior point of the element, its coordinates are basically this n matrix. Okay, so this is a 2 cross 1 vector, so this needs to be 2 cross 6 matrix, and then this x hat. Now what is x hat? X hat is the transpose, so x hat is a vector of 6 cross 1, so it is x1 y1 x2 y2 x3 y3, this whole thing transpose. Similarly, we can represent the degrees of freedom values at any given P as ux and uy. Okay, so just like this, n times u hat. So where u hat is this quantity u1 u2 up to u6 transpose, and we need not mention this, but you should remember this, that Same thing applies to the variation as well. N times V hat, and you can imagine what the V hat should be. So where V is an arbitrary variation with V being a zero vector in gamma u. So wherever the values of u be given, V should be zero. Okay. Achha. So now, how would the N matrix look like? As you can see, the x coordinate only needs x coordinates of the nodal x coordinates. Okay. Similarly, if I were to map ux, I only need u1, u3, and u5. How do I ensure that? So the N matrix, which looks like 2 cross 6, that means it is supposed to have 6 columns, but we only have 3 shape functions. So this is how it is going to look like. N1, 0, N2, 0, N3, 0, 0, N1, 0, N2, 0, N3. Okay. Now you can check that if I multiply that with x hat, okay, I'm going to get this and this expression for x and y values. Okay, and similar result would be obtained when I multiply n with u hat. এই পার্টটা কি বোঝা গেল?
Yes, sir.
Yes, sir.
Okay. Okay. So can you check you are getting what expression are you getting for ux and uy with this multiplication? কি এক্সপ্রেশন পাওয়া যাচ্ছে ux আর uy এর?
So ux হচ্ছে n1 u1 plus n2 u3 plus n3 u5.
ওকে,
আর uy হচ্ছে n1 u2 n2 u4 n3 u6 প্লাস সবগুলো মাঝখানে।
আচ্ছা ঠিক আছে। Okay, now you might recall the principle that we used when we defined shape function for any of the earlier problems, that ni at jth node is actually Kronecker delta, one that populates the identity matrix, which basically means it is 1 if I equals j and 0 otherwise. Okay, so that rule will also apply here. Why do we need any of the shape functions to be 0 at other node? Because you see u1 is sorry, uh, ux is u1 n1 as we obtained, plus u3 n2 plus u5 n3. Okay, so when I move to n1, okay, sorry, when I move to node 1, it should be equal to u1. That means the other, and you see this u1, u3 and u5 all are independent variables. Okay, and if mm, mm, I mean, in my mind, I can think of that both u3 and u5 are 0 and u1 is non-zero. Then also u at node 1 should be u1, which means n1 should be equal to 1. And same thing applies to all other shift functions. Then I can think of that u5 may be 0, u1 and u3 are non-zero. Then if n2 is non-zero at node 1, then it is u1 plus something times u3, which doesn't match the boundary condition. Then n2 should be 0 at node 1. Okay, and this way we can show that each of the shape functions are 0 at any node but their own, and equals to unity when at their corresponding node. And why do we need the okay, yeah, also there is another condition that summation of all the shape functions should be equal to 1. Why do we need that? Because if each node were having the same amount of translation in x and y, then we would expect the entire element rigidly translate. Okay, but if this condition is not satisfied, then it would imply that because of the rigid translation somewhere within the element, some strain is developing. Okay, so that is not practical, which means if the nodes are individually moving like rigid bodies, then the entire element is moving like a rigid body. Okay, so these two conditions must be satisfied. Now tell me, if in this ideal triangle in the natural coordinates, I divide the geometry into 3 segments. Okay, the one opposite to node 1, I'll call that A1. The one opposite to node 2, I'll call that A2. And the one opposite to node 3, I'll call that A3. And please note how I have numbered the nodes. I've always gone anti-clockwise, and there is a reason for that. I'll explain sometime. So let's call them A1 into
So,
A2.
this summation ni equal to 1 will remain valid.
It has to be valid. That's how shape functions
Because
must be.
when we are equating that x equal to 1, n1 is 1. Similarly, for x equal to 2 and 3, we
No,
will have that unity
no, I'll
value of
explain
n.
what this means. Imagine if x1 equals x2 equals x3 equals x star, and y1 equals y2 equals y3 equals y star, then you'd expect the entire geometry to be rigidly translating with a displacement of x star and y star from their earlier configuration. I'm talking about the physical triangle over here. Okay, this is a natural triangle. This is only there for simplification of the calculation. Think of everything in terms of the left diagram. Now, if I write the expression for x at an arbitrary xi eta or arbitrary location, that is simply, as you can see, x star times summation ni, and y equals y star times summation ni. And the only way that interior point P is also having the same amount of displacement as each of the nodes is by having these quantities, this quantity rather, being equal to 0, being equal to 1. If each of the nodes are having the same amount of displacement, then any interior point is also having the same amount of displacement. That's the idea. বুঝা গেল এখানে?
ठीक है.
अच्छा, I'll call the entire area as A. Now please check if this is true. A equals summation AI. That means if I add A1, A2 and A3, that equates to A. You see, the size of A1, size of A2 and size of A3 will depend on where am I taking this point P or P prime for that matter. Okay, বোঝা যাচ্ছে কি বলছি? So can you see that the total area is summation of this individual areas A1, A2 and A3? Can you see this?
Yes, sir.
Yes, sir.
Okay, so number one, this is true. Acha. Now let's say if I define in I of xi eta as AI by A. Okay, then summation Ni is how much? How much is the summation AI? 1.
1.
Summation Ni. Yes, 1. It has to be 1. Okay, because the summation will only happen at the numerator. Acha. Now the next thing. Now what is the value of Ni? Acha, by the way, I made one mistake. I didn't mention the coordinates. Okay, in the natural coordinate. This is how you take it in natural coordinates. It is 1 0, this one is 0 1, and this one is obviously 0 0. Okay, acha, how much is the value of let's say in 1 at node 1, which means if I bring this point P prime, okay, to node 1, okay, so what would be the size of A2 and A3?
0.
And what would be the size of A1?
A.
A.
Which means what would be the value of N1 at node 1?
1.
1. Now if I bring this point P prime either to node 2 or to node 3, or that for that matter anywhere on the line 2 3, okay, what would be the size of A1 if I bring this P prime point anywhere on the line 2 3?
A1 0.
A1 should be 0, right? So 0 1 equals N1 0 0 equals 0. And you can check if I define the shape functions like this, okay, that is true for each and every shape function. Okay, now we are writing the value of N1 at 0 and 1, but we still do not have any polynomial expression of the Ni's. Okay, now for that matter we'll have to calculate the area of the total triangle and also the individual triangles. Okay, can you tell me how much is the area of the total triangle?
Half.
Can you tell me how much is the area AI? Sorry, not AI, A1. You see, coordinate of P prime is xi eta, right? So this distance from the line 2 3 is how much? Xi from the line 2, 3, the distance, the normal distance is 2, 3. Can you see this?
Half xi.
Yes, half xi. So half, because it's a triangle, then the size of the base is 1, okay, because coordinate of 2 is 0, 1, and then multiplying xi. So it is xi by 2, which tells us that n1 is generally xi. And if you do the same analogy, then n2 is eta. But then how much is n3? For that, we'll have to use this logic. There can be only two independent variables, right? Because it is 2D. 1 minus xi minus eta. So these are the three shape functions. Okay. Now you can check whether they are satisfying condition number 1 as well. I have got the expression for n3 by imposing condition number 2, but are they satisfying condition number 1? Okay, so if you check, they are satisfying everything from condition number 1. Now we'll proceed. So we'll now proceed for calculating the strains. Okay. Now আমি পুরো স্ক্রিনটাই মুছে দেবো because I'll have to do a lot of steps. Okay. I hope that's okay. তোমরা হয়তো লিখে নিয়েছো বা ছবি তুলে নিয়েছো বা কিছু মুছে দিলে চলবে তো?
হ্যাঁ স্যার।
ওকে। Okay, so far we needed the geometry. Now this point onwards we don't need the geometry. We have parameterized everything. Okay, the coordinates, the degrees of freedom, we have parameterized everything. Okay, so if you recall, your n kind of looks like this now: xi 0 eta 0 1 minus xi minus eta 0 0 xi 0 eta 0 1 minus xi minus eta. Okay, and if I kind of try to write n as a vector, because there are only 3 independent components. Okay, so that would be xi eta and 1 minus xi eta. Okay, and if I want to represent them as n1, n2, n3, okay, please note these two are different notation. Here I'm trying to write in such a way that once I multiply this n matrix with u hat, I get u vector at any location. That means basically the x and y component of the displacement, where u hat is what we have defined earlier. Okay, similarly we can get the v vector like this, n times v hat. Okay, we are not doing that routine where we would represent v as v transpose n transpose. We are not doing that. Okay, that we do not do in 2D. That is only reserved for 1D. And x also we would write it like this. That means the coordinates x and y at any arbitrary point inside the element is also n times x hat. Okay, now this is how you need the shape functions be written, but your actual shape functions written in vector form, because there are 3 nodes, 3 of them are there, so they are basically like this. Okay, now if I take gradient of shape functions with respect to natural coordinate, okay, Now there are two natural coordinates, xi and eta. Okay, so this is how each of the terms would be written: del n I, del xi j. So I ranges between 1, 2, and 3, and j ranges between 1 and 2. Sorry, and xi1 is xi, and xi2 is eta. Okay, so with that general notation, you see it is just like the gradient we defined for any other vector in our previous two classes. Okay, so with row changes your number of the shape function, with column changes your coordinate. So can you take the gradient and write the expression? So it is going to be, what size should we have? It should be a 3 cross 2 matrix, 3 rows and 2 columns. Okay, so can you populate this 3 by 2 matrix? এটা সবাই বুঝতে পেরেছো তো কি করতে বলেছি? মানে তিনটে শেপ ফাংশন আছে, প্রত্যেক রোতে প্রত্যেকটা শেপ ফাংশনের প্রথমে জাই এর রেসপেক্টে, পরে ইটার রেসপেক্টে ডেরিভেটিভ নেবে, পার্শিয়াল ডেরিভেটিভ। ওকে, same thing applies to the second shape function and then the third shape function. Okay, I hope এটা বুঝতে পেরেছো সবাই। ওকে, হ্যাঁ, কে বলছিলে বলো আরেকবার।
1 0
1
1 0 1 minus 1.
Okay, so this is what the gradient of the shape function with respect to the natural coordinates would look like. But as you might recall, we need the derivative of the shape functions with respect to the physical coordinates. So before that, let us try to define the gradient of physical coordinates with respect to natural coordinates. So you have seen that, so this is going to be a 2 cross 2 matrix. Okay, so it is del xi, del xi j is the expression. Okay, it's a 2 cross 2 matrix. Now obviously you can write down that x is basically n1 x1 plus n2 x2 and n3 x3. Okay, and if you take del x del xi, that would be x1 minus x3. Okay, del x del eta should be x2 minus x3. You can check, you can do that. Okay, but then you can populate, so you can call this one as x13, you can call this one as x23, and so on, and eventually it is going to look like this: x13, x23, y13, y23. Okay. Now that is the simplest way to do this exercise. but I'll do it in a little complicated way so that the approach remains general. The approach remains general. Okay. When you are uh, doing any other type of element. So we can say that I can write this x vector also like this. x1, x2, x3, y1, y2, y3, this thing times our n bar vector. Okay, which means it is just a different representation from this earlier representation to this new representation. Okay, so x1, x2, x3 basically means the same thing. Okay, now if I take gradient of the physical coordinate with respect to the natural coordinate, you see these are nodal coordinates x1, x2, x3, y1, y2, y3, and they are constants. I mean, not constants, but they are like independent of xi and eta. So when you take partial derivative, you don't take partial derivative of these quantities, but instead you take the partial derivatives of the shape functions. Then when what happens is that then you have x1, x2, x3, y1, y2, y3. This multiplying gradient of n bar with respect to xi. So basically this matrix. Okay. Now can you do this multiplication and tell me whether or not you are getting the earlier expression that we got?
Has the same expression.
Same expression, right? Okay. So we'll call this quantity, or we'll define this quantity as the Jacobian. Okay. Now the next thing that you would do is to take the derivative of the shape function to with respect to the physical coordinates. So we define gradient of n bar with respect to x, which basically gives you individual components as del ni, del xj, individual components. Okay, and that basically transfers through chain rule as del ni, del xi k, del xi k, del xi k, del xj. Okay, but this chain rule is not a single term. If it is not clear to you, then by this repetition of index, what I mean to say is there is a summation over k. Okay, so basically what you do, you take partial derivative of each of the shape function, partial derivative of the shape function with each of the natural coordinates. Then you take the derivative of the natural coordinates with respect to the physical coordinates. Now this basically means what I'm trying to do here, summation over k, gradient of n bar with respect to xi. For that I'm taking the ikth term, multiplying that with the inverse of the Jacobian, the kj term of the inverse of the Jacobian. You see, if Jacobian is gradient of x with respect to xi, then the inverse of that should be gradient of xi with respect to x, or individual terms should look like del xi I del xj. Okay, now you are multiplying that with this quantity and then doing a summation over k. Okay, please wait for 2 minutes. Okay, so uh, so from this multiplication, as you can see, this is the formula for getting the product of two matrices. So it is summation over k a I k b k j. What it basically means is gradient of n with respect to xi is gradient of n with respect, sorry, gradient of n with respect to x is gradient of n with respect to xi times j inverse. Okay, so uh, so now can you get the gradient of n with respect to the physical coordinates? So I'm sure you can, okay, but you don't have to do the calculation right away. So you can leave it here, okay. But I need you to note one point with the type of element that we are using. You see, none of the terms are functions of xi or eta. In the Jacobian, none of the terms are functions of xi and eta. Okay, you see this x1, x3, x2, and x3, and everything else, okay, which populate the Jacobian matrix are actually combinations of the nodal coordinates, and the coordinates of the nodes are not functions of the xi and eta. So the Jacobian is not a function of xi and eta, okay, not a function, not a function of xi and eta, and loosely speaking, it is constant. And same thing applies over here, that the gradient of xi is also a constant, which means it's not a function of xi and eta. And similarly, what we have, this product over here is also a constant. Okay. Okay. So how would del n del x matrix look like? Each term would look like this. So first one is del 1 del x, del n1 del x, then del n1 del y, then del n2 del x, then del n2 del y, and then del n3 del x, and del n3 del y. Okay, so if you do multiply del n del xi with j inverse, that means take inverse of this, okay, and which shouldn't be a problem given that j matrix is a matrix of constants. So you would get essentially the product would be this one is 3 cross 2 multiplying again 2 cross 2, eventually giving you a 3 cross 2 matrix. Okay, so you can do that. Okay, now comes the next part. আচ্ছা এই অবধি ক্লিয়ার তো সবার?
Yes, sir.
Okay, so again I'll again clear this screen over here. Now if we are, since we are working in 2D, this is how our strain in void notation looks like. Again, we are using a small strain notation. So it is composed of only three components: epsilon xx, epsilon yy, and gamma xy. What are their expressions actually? This one is actually del ux del x, del uy, the next term is del uy del y, and gamma xy is actually del ux del y plus del uy del x. Epsilon xy is actually half of gamma xy, but as we have discussed earlier, in void notation we use gamma notations and not epsilon for shear terms. and I also mentioned the reason behind that. So if you are not, if you have not seen that, please refer to that. Okay, please go through last class recording of the last class. That should give you the reason why we should be using gamma notations. Now the next term, you might recall that ux is actually not a function of, I mean, sorry, ux is a function of x, but what are functions of x? This one is n1 u1 plus n2 u3 plus n3 u5. So the ones that are functions of either xi or x are the shape functions. Okay, so I can write, let's say the first term, and I can write it to be del n1 del x times u1 plus del n2 del x times u2 plus, sorry, u3 plus del n3 del x times u5. Okay, and so on. Similarly, I can populate the second row, and this is how the second row would look like, and I'm writing all the terms here. The second row would look like this: del n1 del y times u2. Instead of u1, it should be u2. So two things are changing from derivative over with respect to x to derivative with respect to y. And instead of multiplying u1, I'm multiplying u2 because I'm supposed to take derivative of degrees of freedom in y direction. Del y u4 del n3 del y u6. Can you write down the expression for gamma xy? কিরম হবে gamma xy? So just take the first term. Okay, so del ux del y is del n1 del y times what? u1 or u2?
u1.
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 Then del n2 del y times u3. Then
u3.
del n3 del y times u5. Okay, and for the next term it is going to be del n1 del x times u2 plus del n2 del x times u4 and del n3 del x times u6. Okay, so eventually your strain vector in Voigt notation, okay, would look something like this. Okay, so do you get the idea how it is happening? So I'm only picking u1, u3 and u5. Okay, so can you tell me what would be the second row?
0
0, then
del n1 del y,
then
0
then
del n2 del y,
del y, then
0
then
del n3 del y,
acha, the next row
del n1 del y, del n1 del x, del n2 del y, del n2 del x, del n3 del y, Del N3 del X.
Okay. So eventually, just like the one-dimensional case, this would be our B matrix multiplying the U hat vector. Okay. Now, the B matrix has the size of number of components of strain times total number of degrees of freedom within the element, eventually giving you a 3x1 strain vector. Okay. Acha. So similarly, we can define the variation of strain, which is basically this B multiplying V hat. Okay. And if you refer to whatever has been discussed in the last class, so from that you should be able to figure out that how do I get all of these terms, del n1, del n1, del x, del n1, del y, and all these terms. I would get that from this matrix gradient of n bar with respect to x. Okay. So once I calculate the Jacobian, take the inverse of it, and multiply with gradient of n with respect to xi. Okay. So I'll be having the gradient of n with respect to x, and that quantity is populated with each of these terms. Okay. So the terms that are seen in the B matrix are actually coming from this gradient of n with respect to x. Okay. So I'll have to substitute from there. Acha. Now again, we discussed that this Jacobian is a constant. This gradient of n with respect to xi is a constant. This gradient of n with respect to x is a constant, which basically means this B matrix is a constant, right? B matrix a constant is a matrix of constants.
Yes, sir.
Yes, sir.
Similarly, the coefficients of the B matrix, coefficient of each term of the B matrix, that is the U hat vector, that is also a vector of constants. Of course, the displacement of each node would change, but all I'm trying to say here, constant is a loosely used term here. What basically means is not a function of xi and eta. That means not changing inside the element. So U hat is also not, these are nodal degrees of freedom. That means they are also not changing inside the element. So what do I get here is that this strain vector is not changing inside the element. So it is constant within a given element. The strain matrix would be a constant within a given element.
Yes, sir.
Yes, sir.
B matrix is a constant, U hat vector is a constant. So the strain matrix or strain vector is going to be a constant within a given element. Do you see the problem there? Do you see any problem with strain being a constant? Okay, I'll explain that in a minute. Achha. Because strain is a constant, stress, which is some plane stress or plane strain elasticity tensor times strain. Now this thing is also not a function of xi and eta within a given element. So basically the stress is also a constant. Therefore, three-noded triangle element is a CST element or a constant stress element or a constant strain triangle. Constant stress triangle or constant strain triangle. Okay. So, which is a very special situation. Okay. And I'd like to explain the issue with that also. But before going into that, CST element may also refer to constant stress tetrahedron. Okay, and it is very intuitive to figure out what the shape function should be for a constant stress tetrahedron. Do you see what I'm talking about here? It's a 3D element, okay? And constant stress tetrahedron is also a CST element. বোঝা যাচ্ছে এটা?
স্যার যেহেতু দুটো ট্রায়াঙ্গেল মানে ওই জন্য কি মানে অ্যানালজি দিয়ে মানে 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 এটা তো কোনো মানে প্রুফ তো এরকম করে বোঝা যাচ্ছে না যে এটা এরকমই হবে।
এরকমই হবে, is just a simple extension of what we did for 2D. Okay, and in that case we should be actually taking the let's say if I take an internal point, okay, with that I should be dividing the geometry into different set of volumes, okay, and then from the ratios of the volumes I should define the shape functions. Okay, so yeah, I'm not showing the proof here, but you can imagine something like this will happen. Okay. So the 3D version of CST element is a four-noded tetrahedron element. Okay. Acha. Now, how to define the element stiffness matrix? If you follow the last class, we have already defined it to be B transpose D bar B D omega. Okay, where omega represents the volume. Okay, where did it come from? It came from this expression where we are integrating over the volume this transpose epsilon V transpose D bar times epsilon bar D omega, okay, from the variational formulation. Then for this variation of strain, we can write it to be V hat transpose outside of the integration, then V transpose, then D bar, then for epsilon we would write it as B times V, so it would look like, sorry, V times U. So this is how it look like, and this whatever is inside is going to be your element stiffness matrix. So now let's write the expression for the element stiffness matrix. But before that, try to imagine this. Here is a cantilever with a concentrated force at the free end, and what I chose to do is model it with a series of CST elements. Okay, now what do we know about beams, cantilever or simply supported or overhanging, whatever, that the maximum variation of stress occurs across the cross section. It goes from high positive to high negative. Of course, the amount of stress would depend on how much is the bending moment or how far are you from the free end. Now leaving that aside, look at any given element. Let's say this one. Okay. If you try to model it with a CST element, for this entire element, the stress is going to be constant. Same stress. Okay. Okay. What do I mean by that is you are trying to model an entire thickness with a single element. Okay. And let's say even if it tries to give you an average stress, what value of the stress should be? The stress goes from, okay, let's say plus 100 megapascal over here to minus 100 MPa if you solve the problem in a closed form way. But if you are using finite element method and if you are using a CST element, okay, that would probably give you an average value across the entire element. And it seems to me that it would be more dominant towards the compressive side. Okay, so let's say it gives you a minus 30 MPa of average stress and no other value. Okay, so that is the same value everywhere. Not only is that incorrect, that is a very small value of stress compared to the stress that you are seeing at different locations. Okay, many times the failure of a component is dependent on how much stress is developed. Okay, so the prediction of the stress is going to be, or for that matter strain, is going to be really small with this element. And what happens with a smaller strain? The finite element solution, since the stress is small, the strain is also going to be small. The finite element solution tends to be more stiff, like by the use of finite element method, you have made the structure more stiff because low strain means low deflection. You see, if the closed form solution tells you that this deflection is PL cube by 3 EI, you will get something else in the finite element solution if you are using CST element. Pretty inaccurate. And that's why the CST element tends to be very stiff because it doesn't allow for the variation of strain. এই পার্টটা কি বোঝা গেল?
Yes, sir.
Yes, sir.
Okay. আচ্ছা, সো একটা জিনিস খেয়াল করো, how do I write this equation? This equation be written as I would write d omega as dx dy times h, and this dx dy is actually determinant of Jacobian, and this can be shown, and I'm not showing you the identity over here. The dx dy or the differential area can be written as det j times d xi d eta times h. What is h? H is the uniform thickness. You can also assume unit thickness. In that case, it is 1. So what do we have here for d omega? Det j, d xi, d eta, and h. And if xi is the inner integration, so the limits on xi would be function of eta. These are not independent set of integration. Eta changes from 0 to 1 because it's a triangle, unlike a square. Okay, hence the limits are not independent. The limits on xi are 0 to 1 minus eta. For any given value of eta, the xi can only change between so at any given eta, Okay, if I am integrating over this strip, the xi can only change between 0 to 1 minus eta within this strip. Okay, then whatever B transpose dB that you have. Now please note, for CST element, B matrix is a constant, D obviously is a constant. So the entire integrand, including determinant of J, is a constant. So if I write this to be B transpose D bar B, then whatever is det J, D is not D xi, times H, then 0 to 1, 0 to 1 minus eta, D xi, D eta. Okay. So if you do this integration, that basically gives you the area of the triangle in the natural coordinates. So you'll see this is going to give you a value of half. Okay.
হ্যালো
হ্যাঁ বলো।
স্যার, বলছি যে ডি ওমেগাটাকে আপনি কিভাবে লিখলেন, ওটা ডিএক্স ডিওয়াই একটু বলে দিন স্যার।
বলছি, ডি ওমেগাটা হচ্ছে in physical coordinate it is the differential area times the thickness, তাই তো? এই যে differential area in physical coordinate, that is basically d xi d eta in the natural coordinates times determinant of J. So differential volume is differential area times the uniform thickness. So uniform thickness, and this is what is dA. Okay.
ঠিক আছে।
আগের দিন আমরা কি দেখলাম, যে যখন আমরা মানে ডিফর্ম কনফিগারেশন আর আনডিফর্ম কনফিগারেশন দেখছিলাম, so we wrote d small x to be f times d capital X. Okay, now if you look at, you use the same analogy with the natural coordinate and the physical coordinate. Here none of them are deformed or undeformed configuration. Here one is natural coordinate, another one is physical coordinate. So it is going to be J times d xi. Okay. So if you take two differential d xi elements, okay, and do a cross product, then you have a differential area. Okay, so it is going to be J times d xi 1 cross J times d xi 2. It can be shown that this quantity has a magnitude of det J times magnitude of d xi 1 cross d xi 2. So what I'm trying to say here is the area in the physical coordinate, the differential area in the physical coordinate is det J times the differential area in the natural coordinate. That's it. It can be shown. I'm not showing it here. Okay.
ঠিক আছে।
আচ্ছা, Now, what is the value of det J actually? The value of det J is, if you check, is going to be you see, integration det J d xi d eta is supposed to give you the area in the physical coordinates. So det J is actually
2 times
twice the area. Okay. So you can check that also from so from the expression of J, you see it is x13, x23, y13, y23. Okay. Now, so in the physical coordinate, let's say these are the nodes 1, 2, and 3. Okay. And this one, let's say, is the R13 vector. Okay. So if I write J transpose, this is how it looks like: x13, y13, x23, y23. Okay. So the coordinates of R13 are x13 and y13. Similarly, coordinates of R23 are x23 and y23. And this and determinant of this would basically give you the magnitude of the cross product of this to this. Okay. And you know that the cross product actually gives you the, so if you take two vectors, if you take a triangle like this, okay, so draw the parallel lines as well. So the cross product, okay, R13 and R23 gives you the area of the parallelogram, or for that matter, twice the area of the triangle. So determinant of J is twice the area of the triangle. বোঝা গেল এটা?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. So we'll stop here, and in the next class we will continue with the force vector for a CST element. Okay. And today you can have this assignment. So you can try to get so imagine if I divide a cantilever beam, okay, with two CST elements. I'm applying 100 Newton force. The uniform thickness is 1 centimeter. This height over here is 5 centimeter. Okay, and the length over here is 1 meter. So for the sake of simplicity, let's take this to be 10 centimeters. Okay. So first do the closed form solution. For the deflection. Okay. Then try to do the finite element solution. You can assume plane stress. So get the expression for the D bar for plane stress scenario. Okay. And from that, by now you know how to assemble matrices. Okay. You'll probably have to do a global numbering of the degrees of freedom. So if I numbered the nodes as 1, 2, 3, and 4, then the degrees of freedom are numbered like this: U1, U2, U3, U4, U5, U6, U7, U8. Okay, acha. You can take the force to be acting in the upward direction, which is positive for finite element method. Okay, try to solve this problem. Okay, and compare the values of deflection that you get out of two scenarios. Okay, এটা করা যাবে?
চেষ্টা করো স্যার।
এটা একটু চেষ্টা করো। I'm deliberately skipping anything with the distributed load because we have not covered how to get the traction force vector. Okay, but the treatment for you see the the reaction forces and for concentrated forces or the point loads, that is going to be very similar to the one you did for one-dimensional problems, or for that matter beam problem. So you can leave it there. আচ্ছা, একটা জিনিস বলে দিই, 2D এলিমেন্টের জন্য 2D এলিমেন্টের জন্য এখানে কোনো এখানে ডিগ্রি অফ ফ্রিডম গুলো সবগুলোই ট্রান্সলেশনাল। Hence, there is no need for assumption of any rotational reaction, like reaction moment or anything. So this thing would only be associated with forces, and just follow the consistent finite element formulation. Don't try to use solid mechanics here. Okay, and even for the first part of the problem where you are supposed to get the delta for closed form solution, simply use the formula PL cube by 3EI. Okay, don't use anything from solid mechanics. You see, in the finite element formulation we have already incorporated solid mechanics, so it should take care of that. Okay, your job would be to find out the element stiffness matrices. Okay, and you can figure out which of the degrees of freedom are constrained. What I can see that U1, U2, U7, and U8 are constrained. So take the reaction forces for those corresponding values. And what I can also see that at node 3 in the direction of U6 there is a force. So that is the only external force. Rest of them are zero. Okay, so the point loads are going to be like this. The force vector, the one coming from the external force, and the reaction force. So reaction force is going to be R1, R2, then 0, 0, 0, 0, R7 and R8, and the force vector is going to be 0, 0, 0, 0, 0, 100, 0, 0. Okay, those are the only two contributors to the force vector. One is coming from the external source, the other ones are the reactions. Okay, and on the left hand side you have the element stiffness matrices assembled into global matrix. Okay, times the U hat vector, which goes from U1 to U8 equals to F. Okay, so from that try to get the solution for the unknown degrees of freedom, that is U2, U3, U4, U5, and U6, and the unknown reaction forces. Okay, okay, so we'll meet on Saturday. So if you find any issue regarding the problems, you can let me know.